So first of all, let me thank organizers for inviting me to this wonderful place. I'm really happy to be here. And what I want to tell you a little bit is a fundamental feature of multi-band and multi-component superconductors that appears when they break time reversal symmetry. That has been realized only a few years ago, not actually by us, but by some other people. I'll come to that. This is the work done with then my postdoc, Julia Link, who is now at TU Dresden in Germany. And it's mostly described in these two, one short and one very long paper. So I'll tell you a little bit about the general feature of Bogoliubov-Hamiltonian, which you know. So I won't construct anything that you don't know, but I maybe will tell you something that you don't know from Bogoliubov-Hamiltonian that we all know very well. I'll basically try to give you a very elementary reason and derivation of the so-called Bogoliubov-Fermi surface, which is that new feature I want to actually talk about. So the talk will be very simple, focused on only one thing, right? And that is basically how and why exactly, these Bogoliubov-Fermi surfaces in fact emerge. I'll concentrate on our contribution, which is the case without inversion symmetry, that was initially thought to be absolutely crucial actually to obtain these surfaces in the older work by Achterberg et al. I'll come to that. We'll go back to that as well and see that when inversion is present, in fact, there are some nice analogies with special relativity which allow you to actually see why Bogoliubov-Fermi surfaces appear in two lines, essentially. I will not talk about, but I could, about the interesting many-body aspect of this problem, which is basically that in the case of inversion, in fact, residual interactions break inversion spontaneously at much lower temperatures, so you can kind of remove it out of the problem. That would be a much longer subject, and I won't have time to talk about that. If somebody's interested in that, we can talk about it later. So motivation for this, of course, comes from many examples. I have one here. But basically, multi-component superconductors, by which I mean more than one superconducting order parameter, they, in principle, like time reversal symmetry breaking. And the reason for that is essentially that is often the way to actually lower the superconducting energy. Here I have one example which is I'm particularly fond of, but it's certainly one of hundreds, and that is J equals to 2 5-component three-dimensional D-wave superconductor that was known a long time ago to people like Mermin, for example, but recently has been revived by us and some other people, where you have, for example, a 5-component symmetric traceless matrix that is actually a tensor under rotations, and that actually allows you to write down a rather complicated quartic term in the Ginzburg-Abdal theory. My only point here is not really to talk about this, but just to show you that this is a very typical situation where if you actually calculate the phase diagram that depends on these three couplings, you find that in fact most of this phase diagram is occupied by phases that do break time reversal. So for example, both the so-called ferromagnetic phase, which is superconducting ferromagnetic phase, and the cyclic phase, which is not ferromagnetic but nevertheless breaks time reversal, actually break time reversal. The only phase that doesn't is this real phase. So it's a very common situation. Right? So I'll come back to this, but this is not an important part of my talk. It's just an example to show you that basically this is a very typical situation. The time reversal wants to be broken when you have more than one component. So how does this happen? That will be the bulk of my talk. Right? So let's look at I'll show you a real derivation here, actually, how this happens. I think it's completely elementary, and one can teach it basically in a graduate course on superconductivity. So imagine that we are in some superconducting state, and we have multi-band situations, so more than one band. That is crucial, actually, for this to exist. And we wrote down some Bogoliubov-Hamiltonian, right? And we just want to diagonalize it. So all I want to show is that typical Bogoliubov-Hamiltonian for the multi-band superconductor, which breaks time reversal, will in fact show you that they're actually surfaces of zero energy excitations. Right? So I hope you appreciate that this is a very unusual situation. Right? We usually have a gap, so no zero energy excitations at all, or we have points or lines, right? But surfaces are something that one will not actually a priori guess. Right? And why exactly that is connected with the time reversal, that's basically what I want to argue. So let's imagine that we have something like this. And this is some component. This is basically a particle Hall object, or which one could call Nimbus spinor, where I have a fermion operator and basically Hall operator, which I will also form in a somewhat maybe a non-standard way, where I will include this. Basically, this will be just a time reversal of the particle operator. So in other words, I will include in this whole component whatever u I have in the time reversal operator. It's actually the best way to do this, it turns out. For example, this would be sigma 2, right, if I was talking about spin 1/2. Right? But in some general situation, it could be something else. Right? Anyway, this is just some column of creation and annihilation operators of some length of 2n. So this is some big matrix. It could be small matrix, but it could be very big. Its size doesn't matter at all for this argument. So in this particular representation, Bogoliubov-Fermi Hamiltonian basically looks like this, right? So there is a normal Hamiltonian chemical potential. The whole part is just minus normal Hamiltonian without any transverse, no p, minus p, or nothing. That's basically the consequence of pulling out this unitary part of time reversal. And then we have some pairing matrices here. I'll assume, of course, that the time reversal is the symmetry of the normal state. Even that is not necessary, actually, but I'll assume it to be specific. And then the pairing term, right? This is a matrix that sits here that in real space would look something like this. And this is basically now some matrix, because we are talking about multi-component superconductor. This is a matrix, which is a linear combination of some other matrices that span the space of possible superconducting matrices that we can have, which are all even under time reversal. But these coefficients here, of course, can be complex. These are our ordered parameters. Right? So, for example, in the case that I was just mentioning before, there would be 5 of these numbers, 5 complex numbers. So a superconductor would, of course, have only 1. Right? So now we have more than 1. That is crucial. So what is time reversal symmetry breaking in this language? It's basically a relative phase between these deltas. Right? So, for example, if I have one real delta, I need to have something which would be at least complex, if not entirely imaginary, to actually have time reversal broken. So time reversal is preserved if, for example, all of these imaginary parts are 0. Then we have something that is time reversal preserved. Right? It is broken if one of these is not 0, and that will actually mean for this matrix that it is not Hermitian. Right? Of course, whole Bogoliubov matrix is Hermitian, but the pairing matrix will not be Hermitian. So that's the situation. So now imagine that you have some eigenstates of this Hamiltonian, of the normal state Hamiltonian, with some eigenvalues, let's say n of them, whatever number of bands are actually participating in this. Right? And then, since we do not have inversion, we will have just one state at each momentum. Right? Not 2. Right? Although we do have time reversal in the normal state, without inversion, there will be only one state at each momentum, because time reversal connects p to minus p. Right? You need inversion to bring that back to the original momentum and have 2 states. So without inversion, we have only 1. So I'll call one that actually intersects the chemical potential, this red line here. I'll call that a light state, basically, some state that is right at low energies relative to chemical potential. And the rest I will call heavy. Right? These are these other bands, right, that are basically at some finite energy away from the chemical potential. Then we can reorganize our Hamiltonian into basically a 2 by 2 matrix here that has only that light state and its whole double, right? That would be sitting here. And the rest, all of these heavy states, and minus 1 of them would be here. And then there is some coupling between them. That's the same Hamiltonian I was talking about before, just rewritten, reshuffled. Okay, so you just want to understand basically the features of this Hamiltonian, particularly where the 0 states. Right? That's all. So how do we do this? Well, we search for the quasi-particle spectrum. It's a single particle problem. Right? You just need to find the solution of this equation. Right? But of course, you know, the size of this is arbitrary. The Hamiltonian is actually also arbitrary. It just breaks time reversal. So it's not so obvious to what actually solutions of this equation will be. So here's how to think about this, right? So you can write this determinant using the so-called Schur's complement, which is a very useful trick that Isaac Schur actually almost more than 100 years ago figured out. And it's often used in electrical engineering, for example. You can rewrite this determinant as the product of 2 other determinants, where the one involves only the heavy states, and the other involves something that you could call effective Lagrangian. this effective Lagrangian is basically 2 by 2 function of frequency that involves just the light states, the ones that are near the chemical potential, and then inversion of the heavy part. So this is possible to do as long as this inversion doesn't hit 0, right? So I don't get a divergence here. So basically, I would invert this, find the effective Hamiltonian here. If I'm looking at 0 modes, of course, I can certainly do this because heavy modes are away from the Fermi surface. And this can be inverted. And therefore, when this left-hand side is 0, that just means that actually the determinant of the effective Lagrangian is 0. Now, the way to think about that, this procedure for something in condensed matter physics, is that this really is just the same as if we integrated over the heavy modes in the partition function. That would do exactly the same thing. So the Schur complement is actually nothing new for anybody who ever integrated out some modes in a partition function. So we basically need to solve this, right, which is a 2 by 2 problem, but of course involves this inversion, so it's tantamount to solving the whole problem. Okay. So Bogoliubov-Fermi surface is at omega equal to 0, right, if it exists at all, right? And that basically is determinant of something that I will call effective Hamiltonian, which is 2 by 2, and it's essentially effective Lagrangian at omega equal to 0. Okay. It's a 2 by 2 Hamiltonian. We just have to find it, and that will give us where exactly are the 0 modes. Okay. It's a 2 by 2 Hamiltonian, so therefore it's a Hermitian 2 by 2 matrix. I can expand it in terms of the Pauli matrix as a unit matrix. And its determinant equal to 0 essentially means that this is 0. So now we are zooming in on the problem, right? If this is just one condition, and not more than one, it would have to be that this f naught is actually finite. Because if f naught is 0, this is the sum of squares, and it's certainly more than one condition. It would lead to basically lines, points, or even full gap. So somehow this f naught, right, the unit matrix has to show up in the effective Hamiltonian. Does that happen? Well, you can actually see how that might happen even without doing any calculations by thinking a little bit about how these coefficients actually transform under the change of phase of the order parameters. So let's say I change the phase of all the order parameters equally. Right? Then, of course, this f1 and f2, which are off diagonal, do change, right? Whereas f0 and f3, which are diagonal terms, do not change. Right? So that means that if I'm looking at small delta, for example, f1 and 2 have to go like odd powers of delta, whereas f1 and f0 and f3 have to go like even powers of delta. So at small delta, right, this would go like something that is of order delta and delta cubed then, without the delta squared term, where f0 and f2 would have delta squared term as the leading term. So that means that if somehow I notice some direction in the momentum space where this is 0, right, this leading delta term is 0, then in fact f0 and f3 would be larger than f1 and f2. And that's the reason for the Fermi surface. So the picture that one should have in mind is this. I think this is exactly how one should think about this. Right? So imagine I notice some direction where this leading term, direct pairing between the light states is 0. Right? So something that I would think I have a Dirac point, for example, or a part of some line. Right? Now I look at that. In normal state, the situation looks like this. Right? I was plotting that before. In the superconducting state, if delta is small, right, this whole thing will be shifted to the right by f3 term, which is over delta squared. That is not important. But then it will shift it down or up by f0, which is important, which is also over the delta squared. Right? That is this thing here. So it's basically just translated down in this particular case. It could be up as well. And then, of course, there is opening of a gap because the crossing has to be removed. But that we now know is over the delta cube in this particular direction. Right? So basically, the shift downward is always larger than this actual opening of the gap. And therefore, we necessarily end up with these 2 points, P1 and P2, that are at 0 energy. So that is in one particular direction. So you imagine that I change the direction a little bit. From continuity, this P1 and P2 basically have to change, right? But not disappear immediately. Right? So there has to be a surface spanned by these 2 points as I change the direction of this particular momentum where all delta term was 0. So that's the surface. That's basically how the surface forms. And you notice that actually this is a recoupling phenomenon that's delta equal delta reasonably small is essential actually for this to happen, because if delta is big, of course, then this opening of the gap would be larger than this shift, and you would not have the surface. So when the time reversal is preserved, it would have to be that f1 and f0 and 2 are 0, right? So that nothing like this happens, right? That is just a shift in momentum space, but the point is preserved, and it would then end up with essentially a line of gapless points. It would have two conditions on three variables, and it would be a line. So how to prove this? I'll just sketch the proof. Basically, of course, I would avoid the inverting the whole large heavy matrix, because that's exactly like solving the whole problem. The way to think about this is to invert 1 by 1, 2 by 2 matrix that appears in blocks of this heavy part here. Right? Because if you do that, then you never really have to deal with anything more complicated than 2 by 2. Of course, the cost is that you have to track what happens at each iteration. Right? So here I have just a formal expression. Oh, sorry, I pressed the wrong button. I have a formal expression for the determinant ultimately in terms of these iterative determinants that I would get by eliminating 2 by 2 heavy state. And one doesn't really have to do anything to understand what happens, because all that happens is that when time reversal is preserved, I never have to multiply more than 3 matrices, right? Each one of these is either sigma 1 or sigma 3. So when you ever multiply Pauli matrices, sigma 1 and sigma 3, if you take 3 of them, will always give you back sigma 1 and sigma 3. So sigma 2 will never appear, right? And therefore, sigma 0 will never appear either. So time reversal preservation basically boils down to simple multiplying Pauli matrices in this formalism, and immediately tells you that if time reversal is preserved, f0 is identically 0. It can never show up in any iteration, and in the final iteration neither. If time reversal is broken, then of course first iteration actually introduces all the coefficients, and then you ultimately get the effective Hamiltonian, which is 2 by 2 with all the coefficients finite. If delta is small, then you end up with this picture that I just showed you of the shift basically producing the surface. So if I go back to this particular example that I was talking about, for example, that would look like this, right? In this state that doesn't break time reversal, we would end up with some lines of points, which is a common situation. Right? But in the time reversal broken states, there were actually two different states with different symmetries. We would end up with these surfaces. Thing to notice about these surfaces, these surfaces are so small that you would think they're just actually points. They're much smaller than the original Fermi surface. So there is actually a gain in energy still by opening a superconducting gap, right? Because most of the original Fermi surface is actually gapped. But the things that are not gapped are still surfaces. Right? So if you look at low energy penetration depth or specific heat, you would actually see different power laws than if you had, for example, this situation here. So this is one way to think about it. And I'll just go quickly over the situation with inversion, which was in fact the original contribution. Right? This whole phenomenon was discovered by these three gentlemen, Achterer, Bryden, and Tim, in this particular case with inversion. And it seemed at that time, and to us certainly, and to them as well, I think, that inversion was absolutely necessary ingredient for Bogoliubov-Fermi surfaces. This is not true, in fact. Now we know. So let's say that we have inversion, just to show you how this whole thing works with inversion. It is actually even simpler than what I was discussing. Inversion just means that there is additional operator P, which is of course unitary, not unlike time reversal. Squares to plus 1. It's actually observable, right? So it's a Hermitian operator. And most importantly, it commutes with time reversal. This is always the case for all spatial symmetries. So if I look at my Bogoliubov-de Gennes Hamiltonian now, which I rewrote just slightly differently than before, it's the same thing. I just rewrote it in terms of these blocks, sigma 3, sigma 1, sigma 2. Right? These are the superconducting terms. These are the normal terms. One can then notice that irrespective of whether the inversion and time reversal are broken or present or not, one can always actually, irrespective of whether time reversal is broken or not inversion, just time reversal, irrespective of that, one can notice that there is an operator hidden in the problem, with sigma 2 here, and combination of these parity, inversion, and time reversal, that in fact anti-commutes with the Hamiltonian. And furthermore, the square of this operator is actually plus 1. So it's definitely not a time reversal or anything like that. Right? It's basically the particle Hall transformation in another language. Now, crucial thing is that this is, the square of this is +1. Now, when you have anti-linear operator that squares into +1, okay, you are guaranteed to have a, what Messier called in his classic book, a real basis, in which this operator is actually with a trivial unitary part. It is only complex conjugation. Now, this is the best basis to work on when you have an operator like this. In that basis, you see, we have a Hamiltonian that anti-commutes with complex conjugation. So it's just an imaginary matrix, completely imaginary. Could be big, but it's completely imaginary. So now imagine that we have an imaginary matrix, and we now do our procedure of finding the effective Hamiltonian. Now we would basically be inverting these heavy modes. Everything is imaginary. This is imaginary, this is imaginary. Every single entity appearing here is imaginary. And therefore, this result here is also imaginary. Now, of course, it's not 2 by 2 problem anymore. It's 4 by 4 because of inversion is involved. Right? So there are 2 light states at every momentum, precisely because inversion is there. So this is 4 by 4. But I have an auxiliary notion that effective Hamiltonian is actually imaginary 4 by 4 matrix. So what is that? Right? It's a generator of SO4 in fundamental representation. Right? I can write it in terms of 6 coefficients, A and B, in terms of some 6 matrices, N and J. Okay? And this is the problem that is well known. Right? Basically, the Hamiltonian looks just like the electromagnetic tensor, of course, just with the imaginary part in front. And this A and B I can think of as electric and magnetic fields, fictitious, of course, in the momentum space. What else do I know about SO4? Well, I know a lot about it. For example, SO4 Lie algebra factorizes into SO3 cross SO3. Right? In terms of these matrices that I wrote, I can actually form linear combinations of them and break SO4 into SO3 cross SO3. This is a well-known thing, for example, in Dirac equation. And in Lorentz basically gives you a classification representations of Lorentz algebra. So this is a completely classical thing, as well known as basically algebra of Pauli matrices. Now, in our problem, what this means is that I can immediately write down the spectrum of this matrix without any calculation. It looks like this, right? Because everything boils down to the calculation with Pauli matrices. So I see immediately that this is 0, right, when single condition is satisfied. A times B, both of these are vectors in momentum space, dot product is 0. Right? So I have single condition and therefore a surface right away. Now then I connect this to what Achterberg, Brygon, and team were talking about. They were talking about that that the effective Hamiltonian has a determinant which is positive, and therefore one would think that there are no 0 modes. But effective Hamiltonian is such, according to them, that it allows the introduction of the Pfaffian, which is the square root of the determinant. And that could actually change sign. That was basically their argument. Now we see that this Pfaffian is in fact exactly this product. Right? So of course this is analogous to what they're saying, but I think it's a slightly more economic point of view, in my opinion, to think about it like this. So the problem then becomes, why is this sometimes 0 actually, and what does that have to do with time reversal? Well, it turns out when time reversal is preserved, there is additional operator that in fact forces A and B vectors to be always either parallel to parallel. So they're never orthogonal to each other and there is no surface. In that case, we again end up with a line and the spectrum basically looks like this. So let me then slowly conclude. So my point is that when time reversal is broken, in the multi-component, multi-band superconductor, rather generic situation, with or without inversion, effective Hamiltonian is the way to think about what happens near the chemical potential. And you would get it from integration over heavy states, for example, and typically end up with small surfaces of 0 energy modes. Small in the weak coupling limit. Of course, everything actually applies to weak coupling limit because if the delta gap is not small, then in fact there may not be any surfaces by the same logic. But inversion is actually not essential for this to happen, as we thought before. I apologize. When inversion is preserved, in fact, if we look at the original if you look at the original problem, we see that the effective Hamiltonian, which is now just 4×4 matrix, is in fact a generator SO4 algebra about which we know everything, and without any calculation, we can immediately see why, in fact, and when there are Bogoliubov-Fermi surfaces is essentially related to the structure of the SO4. The part that I will not talk about is the many-body aspect. As I said, it turns out that when you have inversion, in fact, it can become spontaneously broken by residual interactions in a superconducting state and removed, therefore. So one actually goes to the point number 1 without inversion. The surface, at least in the examples that we could work out explicitly, the surface does not actually disappear entirely. It just gets smaller, and the inversion gets broken. This is the aspect of the problem which I find, in particular, quite interesting. But of course, in a half-an-hour talk, I don't have time to talk about this. I think I can end here. Thank you.
Thanks for your nice talk. Any questions?
First question is sort of obvious question. Which systems have been discovered where this is seen?
This is not seen in any system just yet, as far as I know. So there are, I know maybe 3 or 4 compounds. I'm not a great expert on materials, but I do know 3 or 4 compounds which are multi-component and are believed to break time reverse. However, they all seem to show a full gap. So they simply don't fall into this category.
So maybe the gap is too big?
It just seems that it is that the whole surface is gapped, and there are no zero modes at all in these particular.
Okay.
But of course, there are many non-center symmetric superconductors. So.
My second question is a purely theoretical one. Now that you have again Fermi surfaces, wouldn't there be another Cooper instability possibly?
That's a wonderful question. That actually, you can think of this spontaneous breaking of the inversion precisely in that language. This is analogous of an additional Cooper instability in presence of this surface. When you don't have inversion, then there is actually no Cooper instability that we could think of. And that seems to be completely stable because there is simply no symmetry left to be broken. Everything is already broken.
Funny.
Thanks for your presentation. I'm an experimentalist, and we have been looking for time reversal symmetry breaking superconductor for a couple of years, let's say, but it's a bit frustrating because there is no guidance. So we have looked for non-center symmetric for superconductors with high spin orbit coupling, for superconductors with multibands. So in your experience, what will be, let's say, the best candidates, or where to look for? What is the guidance? Because if I understand correctly, these have high chance for breaking time reversal, but not any multi-band superconductor.
That's right. That's right. You're absolutely correct.
What can you comment on this? Or,
absolutely correct. Absolutely correct. In fact, I'm always puzzled that there are not many time reversal broken superconductors. One would a priori think there should be hundreds of them, right? But in fact, there are only very few, if any. That's right. So there is a mysterious superconductivity appearing, for example, in yttrium platinum bismuth, which is a spin orbit coupled material. And weak coupling calculation there would suggest that time reversal is for sure broken. On the other hand, the penetration depth measurements from Maryland, for example, do not agree with this. They show the power law, which would correspond to the time reversal preserved state. But that would somehow imply that the superconductor is strongly coupled, which it almost certainly isn't, because they can actually estimate, for example, the number of carriers and delta and so on. So I would imagine that there one should actually, for example, have a time reversal symmetry breaking. But even that is questionable. My expectation would be that. But on the other hand, it's not there just yet in the actual lab. So yes, I completely agree. I also mention maybe that the surfaces are hard to see because they're small and very hard to distinguish from a point, for example. Right? So if you measure actually, for example, specific heat or anything that has a power law in temperature, you would see a power law that corresponds to a point, unless you see at very small temperatures some different power law. But of course, at small temperatures, there are impurities and everything hits. I mean, comes into the problem. So it could be easily masked by something. Please.
Ginsburg-Landau equation from your approach. Ginsburg-Landau equation from your approach.
Ginsburg-Landau is basically, you mean the free energy? Ginsburg-Landau free energy? Is that what you mean?
Yeah.
Yes. So Ginsburg-Landau free energy would basically be something that would tell you whether the time reversal is broken or not. So for example, this is something that we can actually derive for yttrium platinum bismuth. We derive these terms, and as they depend on temperature, right, these coefficients, and here's actually this insert has to do with the third coefficient, right? So, but that basically you minimize this, and then you see what kind of configuration actually minimizes the Ginsburg-Landau. That tells you whether time reversal should be broken or not. And typically in situations like this, coefficients are such that in great majority of cases, time reversal is broken. So theoretically, of course, you can derive this typically in a weak coupling scheme, right? Theoretically, you would think that whenever I have more than one component, I always have time reversal broken. So for example, in good old days of high TC, people talked about D plus ID, D plus IS. That I is breaking of time reversal. Right? It always basically gains you energy. But on the other hand, just as we heard now, experimentally, it is not common. So that's already a puzzle. Please.
It doesn't matter which wave function, which spinor are you using for, I mean, it can be Nambu or non-Nambu arbitrary spinor. Does it mean that there are different, it's possible to reproduce similar band structure in different system? Like, for example, Nambu is used usually for Majorana, right? And then Nambu spinor, for example. And in principle, you can put any spinor structure, and the band structure will be a spectrum. The spectrum will be the same. Does it mean?
Actually, so Nambu is not just for Majorana. You would basically, you know, when you look at the BCS spectrum, SY superconductor, you do exactly this.
Yes.
Right. So you have a two-component psi here, and then you basically take sigma 2 times that two-component psi. You have a 4-component particle Hall operator, and that's essentially you diagonalize exactly this, and you find a full gap, right?
I see.
So you can do that in any situation, right? So that there is doesn't have to be spin 1/2. It could even be integer spin.
So this was my question. So the approach, in some sense, universal and allows to reproduce this kind of band structure for different systems.
That's right.
I mean,
that's right.
Independently.
There is nothing else assumed than what I actually explicitly
Yes.
said.
That was my question.
So there just has to be more than one band. It's not enough to have just one band.
I see.
Because you have to have something to integrate over, right? To produce this effective Hamiltonian.
Yes, exactly.
If your effective Hamiltonian is the same as your original Hamiltonian, there is nothing.
I see.
Right?
I see.
But this part here, right? This inversion of the heavy parts. So you have to have some heavy bands that will actually give you the Bogoliubov-Fermi surface.
I see. The final question is: I suppose that your co-author in your publication was Stephen Bircher, or
my co-author is Julia Link.
No, another, you showed another reference where Stephen Bircher was.
No, there is another Bircher.
Another Bircher. It's not.
And his name is actually the same as mine, Igor Bircher.
Oh, Igor. I see.
He's a professor in Alberta.
I thought that he's a co-author.
There is also Stefan Bircher, but that's not him.
I see. So this.
Yes, thank you for pointing out. There are actually two Birchers, if you can believe it.
Thank you. Any questions? If no questions, let us thank speaker again.
Thank you.
It was nice
Thank you
talk, and award him a certificate about attendance.
Oh, thank you. Okay.
Which can be put in somewhere in your office.
Yes, I'll definitely do that. Thank you.
Thank you. Then the next speaker.